In this video, we discuss the error that appears in Euler's method. We'll see that there are two types of error that result from this process. Suppose the function we're looking for is this. For Euler's method, we'd have this initial value and no other points on this graph. Euler's method builds up an approximate solution by approximating it on one interval, then another, and so forth. For the sake of discussion, suppose we didn't only have a single value. Suppose that going into the problem, we knew the exact value of the function at each of these endpoints. Then we could linearize at each of these points like so. This would give us an approximation of the function. The approximation wouldn't be perfectly correct because these linearizations aren't perfectly correct. The curve is not actually a bunch of straight lines. So for example, here, we've got a real value, and we've got the value we get from this linearization, and they are not the same. This error is called local. If we had only local error, we could approximate the function on the entire real number line, because local error does not get worse over time. This approximation over here is just as good as this approximation over here. However, the actual situation is worse. We don't have all these values. We only have this initial condition. So let's let this be the curve we're looking for. This is the only value we know, the initial condition. And let's break the interval into steps. We linearize around this initial condition. We get some local error. Now, on this interval, we want to linearize around this point, but we can't. We don't know what this point is. we have to linearize around this point instead. So now we have a new source of error. Not only are we getting local error because we're linearizing, we're not even linearizing around the right points. This error is called cumulative error. And cumulative error gets worse with time. Due to cumulative error, our approximation over here on this interval is worse than our approximation over here on the first interval. Our approximation on the next interval will be even worse. At some point, our approximations will become so inaccurate that they're useless. We've seen Euler's method and discussed the error inherent to it. It is possible to reduce error, but at a cost. In particular, the only thing we can do to reduce the error in Euler's method is to reduce the step size, what we've been calling h. But making the step size too small will cause Euler's method to run too slowly to be useful, as well as magnifying the rounding error inherent to machine arithmetic.